some examples. So maybe we'll do 3 examples, 2.3, 2.4, and 2.6. And from the next lecture, we'll start chapter 3. So you guys can read example 2.3. So what it says, and then we'll start solving this example. So this example 2.3 is beams in series. So you have beam 1 and then you have beam 2, which is connected in series. You know. So the entire thing is called a system. So this system has two beams, beam 1 and beam 2. And the system of two titanium alloys. So the beams are made up of titanium alloys, so we can extract some material properties. So for example, we know the modulus of elasticity of this titanium alloy is 115 into 10 raised to the power 9 Newton per meter square, or 115 gigapascals. And then we also know the yield stress, like the maximum stress this material can take without yielding, which is 830 into 10 raised to the power 6 Newton per meter square, or 830 megapascals. So these are the two material properties. If we know strain, we can calculate stresses. If we know stresses, we can calculate strain by using this modulus of elasticity, which is a material property of titanium alloy. We also know that the maximum elastic strain, elastic stress this titanium alloy can take is 830 megapascal. So if you apply a force that's going to exceed these stresses, then this titanium alloy will yield. So that's the maximum stress the titanium alloy can take without yielding. So that's the yield stress. They've also given dimensions. So these are square cylinders. This beam 1 and beam 2, the cross sections is square. So the length is LX1 is 10 centimeter. And it's a square, so I'm going to draw a cross section of this titanium alloy here. I'm going to draw a cross section of this titanium alloy here. So this is a square titanium alloy with dimension of 0.7 centimeter. This one. And so the first beam 1 has a length 10 centimeter and it has other dimension 0.7 centimeter. And the beam 2 is also 10 centimeter in length, and the other two dimensions are 0.4 centimeter and 0.4 centimeter. So we have to find these three things. We have to determine maximum force that can be applied without yielding the system. So we have to calculate maximum force. And the second part is we have to calculate strains for each cylinder at yield. So we have to calculate strain for the beam 1, and we also have to calculate the strains for the beam 2. And we also have to calculate lengths of each cylinder at yield. So we also have to calculate the final lengths. So I can just quickly repeat. So it's a system of two titanium alloy square cylinders This is 1 and this is 2, and these are square cylinders. So the dimension of the square of for beam 1 is 0.7 centimeter and 0.7 centimeter. And for the titanium alloy beam 2, the dimensions are 0.4 centimeter into 0.4 centimeter. So the first question is calculate maximum force. The maximum force this system can take without yielding. So we know some formulas for the force. So we know stress is equal to force per unit area. So if we have to calculate force, that's going to be equal to stress into area. So since we want to calculate the maximum force, so that would correspond to this yield stress. So if we use yield stress here, the force we will get is the maximum force, because if you apply force more than that force, then the system will yield, and we don't want the system to yield, so that's going to be the maximum force. So let's talk about beam 1. So F maximum force for beam 1 would be equal to yield stress yield into area. So I'm gonna draw this section here. Fixed support 10 centimeter. This is also 10 centimeter. So we're talking about this part. So what you think the area would be? So if you have a force, the stress we know is 830 into 10 raised to the power 6 Newton per meter square. And what would be the area for section beam 1? Yes. How much? Okay. You've already calculated the area. Okay. Let's see. I'm gonna calculate. But I want to know, like, either we have to use 10 or 0.7 or 0.7. Yeah. Correct. So the area is 0.7 into 0.7. Because it was centimeters, so I divided by 100. So why we have used 0.7? I mean, if you have if the force is applied, so that's the area we're going to talk about, right? So this was 10, and these two other dimensions were 0.7. So I think the most important for you guys is to understand, like, what are the dimensions for the areas. So this meter will cancel out. So the maximum force for beam 1 would be equal to 40670 Newton. So if you apply this much amount of force, the system will almost yield. So if you cannot apply force more than this, because then you will have permanent deformations. So that's the maximum force you can apply. So let's talk about beam 2. Max 2 is yield stress into area. Yield stress we know 830 into 10 raised to the power 6 Newton per meter square. And what would be what's the area for the beam 2? Yes.
0.16 meters squared is 0.4 times 0.4.
Okay, yeah, good. That's correct. So the area is 0.4 into 0.4, 100 into 100. So the force I'm getting, which is gonna cause yielding in the beam 2, is 13280 Newton. So the question was determine the maximum force that can be applied without yielding the system. So we don't want the entire system to yield. So if you apply 40,000 something force, it's going to cause yielding in beam 1. But if you apply a force 13,280, it's going to yield beam 2. But we have to give one force because we don't want the entire system to yield. So we're going to select the maximum force or the minimum force. What's the answer? So we have to select one of these two forces. Yes. Good. So that's the answer. Because if we will select this force, that's higher than this one. So beam 2 will yield at this force already. So that's the answer for part A. And part B is we have to calculate strains. So we know the formula for strain is elongation divided by length, but we don't know elongation. There's another formula which is stress divided by strain. And we know what stress is. Stress is force per unit area. So we can put this here. So I'm going to use this equation. So modulus of elasticity is force divided by area into strain. So since we have to calculate strain, I'm going to move strain in one side and all the rest of the variables on the other side. So it's going to be force over A E. So we know the force, we know the area, we know the modulus of elasticity, so we can calculate the strains. I could not use this equation because I don't know the elongation. So I use this equation instead, like modulus of elasticity equation, which is stress over strain. And stress we know is force per unit area, so instead of stress, I've replaced it with force per unit area. So that's the formula for strain. But we have to calculate strains for both the beams, beam 1 and beam 2. So let's talk about beam 1 first. So strain for beam 1 would be equal to force divided by area into modulus of elasticity. So what would be the force is important to know, and what is the area is also important to know. And modulus of elasticity we already know. So I'm going to put the value of modulus of elasticity. So modulus of elasticity is 115 into 10 raised to the power 9 Newton per meter square. So what is the force? So the force is 13280. because that's the force. We're not going to apply forces more than this because that's going to yield the system. So now we have selected this force. That's the maximum force that can be applied. And now we can calculate under this force what are the strains in the beam 1 and in the beam 2. So for the beam 1, what is the area? So the area is 0.7 into 0.7. And since it's centimeter, so I'm gonna divide by 100 two times to get meters. And this is also a force, which is Newton. So this is Newton. So it's gonna cancel out. So strain doesn't have any unit. It's a dimensionless property. So if you do the maths, you will get strain as 0.002356. Now you can calculate for beam 2. So the beam 2 would be equal to force divided by A to E. So that's the maximum force. So the maximum force is 13280, and the modulus of elasticity is 115 10 raised to the power 9 Newton per meter square. This is Newton. So what would be the area for beam 2? Yeah, that's correct. That's correct. 0.4 into 0.4. And I have multiplied by 100 two times to get 2 meters. So everything is going to cancel out. So the strain is 0.00721. So the last part, it says calculate length of each cylinder at yield. So we have to calculate final length. So we know we have already calculated strain. So we know the formula for strain is elongation over original length, or change in length over original length. And change in length is final length minus original length. So if you rearrange all this, you can calculate the formula for final length, which would be equal to strain into original length plus original length. So we are interested in calculating this final length. So if we talk about beam 1, final length for beam 1 would be strain into length of beam 1, original length. So what is the strain for beam 1? We have already calculated 0.002356. And what is the length for beam 1? Yeah, yeah, yeah. Good, good, good. So it's 10 plus 10. So you're gonna get the value 10.0235, and since the unit was centimeter, so that's. And for beam 2, final length for beam 2 would be equal to strain to L2 plus L2. And we have already calculated the strains, which is 0.00721. and the length is same. So it's like 10.072 centimeter. So you can see the final length for beam 2 is larger than the final length for beam 1, and it makes sense because the beam 2 has a shorter cross-sectional area, so it's going to elongate more because it doesn't have that more higher resistive cross-sectional area. Next, we can do example 2.4. So you can read example 2.4. It says it is a brass pin with a diameter 3 millimeter and the length is 3 centimeter long, and it's confined within two large steel plates, and the plates are then pulled apart. So it's going to generate some stresses, and we have to calculate the maximum force. Should I move to example 2.4? Okay. All right. So this is an example 2.4. It says an annealed brass pin. So you have a brass pin, so we can calculate, we know material properties for the brass pin. So the yield stress for the brass pin is 100 megapascals. So 100 megapascal mean 10 raised to the power 6 pascals, or 100 into 10 raised to the power 6 Newton per meter square. And this is the brass pin. So I'm going to draw this pin here. So that's the brass pin. And the diameter for that brass pin is 3 millimeter. And the length is 3 centimeter. And it is confined by two large steel plates. So it's actually inside these two steel plates. And we have given the dimension of the steel plate, which is 4 centimeter. This dimension is also 4 centimeter. And the thickness is 3 millimeter. These are the dimensions of the steel plates. These plates are then pulled apart. So one plate is being applied a force in this direction, and another plate is being pulled in this direction. So you can see there are forces being applied on the brass pin by these steel plates. So if you look into this annealed brass steel plate, there is one force which is being applied in this direction. There is another force which is being applied in this direction. by these steel plates. So it says if the brass pin yields when an average stress equals half of the yield stress. So basically the yielding, so it's gonna yield at half of the yield stress. So it's gonna yield at half of the yield stress, 50 megapascals. So that's the stress, the maximum stress we're gonna apply. So we have to calculate the maximum force that can be applied at this stress level. So the question is calculate maximum force, Fx. So we know stress is force over area. So we know if we want to calculate the force, we have to multiply the stress with the area. Stress we know is 50 megapascals, which is 10 raised to the power 6 Newton per meter square. The question is, what is area? If we can figure out the area, we can just input the values and we can calculate the maximum force. So the first question is like, is this force a normal force or a shear force? I mean, is it gonna create normal stresses or shear stresses? So we know if force is applied like this, then it's gonna cause normal stress. And if the force is going to be applied like this, it is gonna cause shear stress. So in our case, what do you think? Is it like shear stress or is it like normal stress? Shear stress, yes. So this is our case. Now the question is, what would be the area? We already have the length, which is 3 centimeter. We know the diameter, which is 3 millimeter. We also have the dimensions for the brass, like 4 centimeter to 4 centimeter. So what should be the area? So we know shear stress. Stress is always force per unit area, right? So the area is that cross-sectional area where the force is being applied. So for example, if it's a normal force, so that's the area, right? And if it's a shear force, then that's the area. So the cross-sectional area where the force is being applied is the area we have to consider. So that's the area, cross-sectional area of a circle. So the answer is, what is the area of a circle? It's pi r square or pi by 4 d square. So I'm going to put pi by 4 d square. So there are so many other dimensions given to confuse you guys, but you have to use diameter actually. So you have to calculate the area, cross-sectional area, which is the diameter of that brass pin, and you're going to use that area. Into 10 raised to the power 6 Newton per meter square into 3.14 by 4, and this is 3 millimeter. I'm going to convert it into meter. And then it's going to be meter square. So the force would be equal to 353.25 Newton. So that's the force which I'm getting. So that's the maximum force which can be applied. If you apply a force more than this, then it's going to cause yielding and permanent deformations. So that's the maximum force you can apply. So that's the result. So I think in these type of questions, you have to just figure out which area to select, which force to select, which stress to select. So if you know what are the difference between the normal stresses and shear stresses, and which area to select, like in shear stress and normal stress, then I think these questions are easy. So for normal stress, that's the area to consider. For shear stress also, that's the area to consider. So now we can do last example, example 2.6. So example 2.6 says it's a cold rolled brass beam and it has dimensions 7 inches length, base is 4 centimeter, thickness is 1 by 16th of an inch, and the beam is fixed to a rigid plate at a base, and the force is also given, which is 150 Newton. And we have to calculate these three things. We have to calculate shear strain, we have to calculate the deformation, and we also have to calculate the shear stress in at the base. So I'm gonna go to example 2.6. So last time we calculated stress strain curve for a material when the material was applied, put in a machine, and the force was a normal force. So that's a normal force actually, normal force. So when you have a normal force, stresses are directly proportional to strains, right? And we can remove the proportionality, put a constant. So modulus of elasticity is stress over strain. We already know this. But what happens when instead of normal force, you apply shear force and then you calculate the curve you will get would be for shear stress and shear strain. So let me write this here. So modulus of elasticity is stress over strain. We already know that. This is elastic modulus of elasticity. This is normal stress. This is normal strain. So we know stresses are directly proportional to strain. This is normal stress. This is normal strain. And this equation is true only in the elastic range. Similarly, like normal stresses are directly proportional to normal stress. Similarly, normal shear stresses are also directly proportional to shear strain. This is shear stress and this is shear strain. And this is also true for the elastic range. So we know shear stress is directly proportional to shear strain. If we remove the proportionality, we need to put a constant. So for normal stresses and strains, I put E. For shear stresses and strain, I will put the value G. So similarly, elastic modulus of elasticity was the ratio between stresses and strains, normal stresses and strain. And G is also a ratio between stresses and strain. But in this case, this is shear stress. This is shear strain. And we can call this shear modulus of elasticity. So basically it's the same thing, like ratio between shear stresses and strain. But if it's normal, we're gonna use E symbol. And when we're talking about shear stresses, we're gonna use G symbol. So these are two different material properties. The values are different, but basically the idea is the same. So the question is, consider a cold rolled brass beam. So this is a brass beam. So since it's a brass beam, we can know the material properties. We know E for this, we know G for this, we know the yield stress for this. So since we are talking about shear stresses, so I'm gonna give you guys the G value for this, which is 40 gigapascal. So in exam, I will give you these values. And in the homeworks also, whenever like you have to do the calculations using material properties, the material properties are given. So the length is 7 inches. So this length is 7 inches. The base is 4 centimeter. So this base is 4 centimeter. And the thickness is 1/16 of an inch. So this is thickness, which is 1/16 of an inch. The beam is fixed to a rigid plate, so it's a fixed support. You can say it's a fixed support, rigid plate, and the force P is 150 Newton. So the force which is being applied is 150 Newton at the top as shown. So the first question is we have to calculate the shear strain. So I'm gonna draw this here. Fixed support. So the length is 7 inches. This is 4 centimeter. The thickness is 1/16 of an inch. The force which is being applied is 150 Newton. So the first part is determine shear strain. So we know modulus of elasticity is stress over strain. Shear modulus of elasticity is shear stress over shear strain. So we can use this equation, which is kind of the same as before, but we have used different annotations for shear stress and shear strain. So shear strain would be equal to shear stress divided by a shear modulus of elasticity. We know shear modulus of elasticity, but we don't know shear stress. We have to calculate shear stress. But we know what formula for shear stress is, which is force per unit area. So we can put this formula here. So shear strain would be equal to force per unit area into modulus of elasticity. Or what we can do is we can calculate stress separately and then we can put here as well. So let's calculate shear stress first, which is force per unit area. Force we know is 150 Newton. What is the area? So if you can figure out the area here, then I think you can calculate the shear stress. So you can think what area is. If you have a force which is being applied, normal force being applied, so we know this is the area of concern. So if you have shear force being applied, so that's the area of concern, right? So in this case, what should be the area? That's the area, which, because the force is applied, it's a shear force, and for shear force, we have to consider the area which is parallel to the force being applied. So that's the area which we need to consider. So that is 4 centimeter into 1 by 16 inches. So we have to convert this also. So let's convert inch into, so 1 inch is, let's convert to millimeter, is 25.4. If you multiply with 25.4, you're gonna get millimeter, 25.4. So the thickness is 1.5875 millimeter. We can also convert this inch into millimeter. That is 177.8 millimeter. So the area would be 40 multiplied by 1.5875 millimeter into millimeter. And if you want to convert millimeter into meter, you're gonna multiply by 1000 two times. So stress would be equal to 2.36 into 10 raised to the power 6 Newton per meter square. 2.36 megapascals. So now we know the stress. Now we can use this equation to calculate the strain. So 2.36 into 10 raised to the power 6 pascals. And the value of G is 40 into 10 raised to the power 9 pascals. So the strain is 5.9 into 10 raised to the power minus 5. So I think in this example, the most important was like which is the area to select. Others, we're just using formulas. Part 2 says determine the distance at the top of the beam. So we have to calculate the distance at the top of the beam. So when the force is being applied, what will happen? You will see a deformation, right? So you're applying a force, so it will have angular distortion as well because it's a shear force. It's going to cause shear stress, and because of the shear stress, you're going to see angular distortion. So if this is our brass beam, if you will apply a force, the brass beam will have angular distortion. And we know what this distance is. This is u of x. And this is what we have to calculate. So we know what shear strain is. Shear strain is change in length by original length, or u of x by original length. So then we can calculate u of x, which would be equal to strain into length. Does it make sense, or? So u of x would be equal to strain 5.9 into 10 raised to the power minus 5. And what would be the length? Length would be 177.8 millimeter. So u of x would be equal to 0.01 millimeter. So that's the distance, that's the amount of distance which will be moved by this applied force, 150 Newton. The last question is determine shear stress. Shear stress, and we have to calculate shear stress at the base. And we have to calculate shear stresses in terms of PSI. So we have already calculated shear stress, but they're asking us to calculate the shear stress at the base. We have calculated the shear stress at the top. So if you want to calculate shear stress at the base, you need force at the base, like a reaction force. And the reaction force you can calculate using equilibrium equation, but there's only one force, so I think that's the reaction force as well. So that's basically going to be the same force. But that's in megapascal. They want us to calculate in a PSI, which is pound per square inch. PSI is basically pound per inch square. So I'm going to give you the conversion factors. 1 Newton is 0.2248 pounds. And 1 meter is equal to 39.370 inch. So using these two conversion factors, you can calculate you can convert the force, which is in megapascal, to PSI. So the stress at base would be equal to 2.36 into 10 raised to the power 6 Newton per meter square. And I'm going to change Newton and meter into these values. 2.36 into 10 raised to the power 6. 1 Newton is 0.2248 pounds. And 1 meter is 39.370 inch. So 2.36 into 10 raised to the power 6 into 0.2248 pounds divided by 39.370 whole square into inch whole square. So if you do the math, you're going to get 342 psi.